Recording. Okay, so thank you very much, Professor Usoskin, for joining us. And hopefully in the future, you will be able to visit us and give an in-person seminar. So our speaker today is Professor Ilya Usoskin, who has graduated in 1988 with a master's in space physics a degree from Leningrad Polytechnic School. And he also obtained a degree in astrophysics from the Eye of, if I'm pronouncing it correctly, Physical Technical Institute in St. Petersburg, Russia in 1995. He later received his PhD degree in space science from the University of Oulu in Finland in 2000. He has a tenure as a professor in Lund University, but then he also returned in the University of Oulu, where he became a full professor of space physics, Faculty of Science in 2012. Since then, he has also spent some time as a visiting professor in several institutes in Europe, like the Institut de Physique du Globe de Paris in France, and then in the National Research Nuclear University in Moscow, Russia. Over the years, he has held several prestigious positions, like being a vice director of Resolve Center of Excellence of the Academy of Finland, and he has received numerous awards, including the Knight's Cross of the First Class of the Order of Lion of Finland in 2013, the Julius Bartels Medal of European Geoscience Union in 2018, and an award of the University of Oulu for outstanding contribution for research, and several others. So his research interests lie in the field of cosmic rays, as you might guess from the title of the talk, solar physics, space climate, space physics, geophysics, but also astrophysics. He has published more than 300 articles. He has written chapters in books and invited reviews. And during his academic career, he has supervised more than 10 PhD students, if I'm not mistaken. So we are very pleased to have Professor Usoskin today with us. And with that, I would like to give the floor to you.
Thank you for inviting me. It's a pleasure and honor for me to give a lecture, and the topic is cosmic rays at Earth. Since the lecture is relatively short, 1 academic hour, I will do it very concise, and if you will have further questions, you can ask or read more about that. So I will basically give an overview of what we know about cosmic rays at Earth. And the outline of the lecture is, I will very briefly say what are cosmic rays, what are solar cosmic rays, how can we measure them, what happens to cosmic rays in the atmosphere, and then what happens to the atmosphere under the influence of cosmic rays. Let us start first from the very basics. What are cosmic rays? And I will start from the history of discovery. And actually, it can be traced back to the turn of 19th and 20th century, when C.T.R. Wilson discovered the permanent ionization of air using a very simple device called electrometer, which is shown here, which measures actually the conductivity of Earth. And it was discovered that everywhere on Earth there is some conductivity of air, implying that there are ions in the air. And since at that time it was discovered also the phenomenon of radioactivity, it was believed that the ionization of air comes from a natural radioactivity of Earth, which is partly true, but not the full story, as several years later, Victor Hess, a German physicist, launched an electrometer aboard a balloon to altitude of several kilometers, and first the ionization rate in the atmosphere decreased as expected for the natural radioactivity of the Earth up to about 700 meters, but then surprisingly it started increasing with altitude, which points to the space origin of the atmospheric ionization. It was very easy to show that the ionizing radiation did not come just by sunlight, because similar experiments were done during the nighttime and in different locations. So it was shown that there is always some very low level of ionization in air. It comes from space, from all directions, not only from sun, and the source was called cosmic rays at that time, because physicists didn't know exactly what causes them, and they thought that these are rays like gamma rays, which were of course known by that time. But the name was quite confusing actually, because what we will learn now, cosmic rays are not rays in a sense how we would understand rays. So they are not like sun rays, but they are particles. They are nucleonic charged particles, actually nuclei or atoms fully stripped of electrons, so only new nuclei ranging from a single proton, which is a nucleus of hydrogen, and they compose around 19% of cosmic rays. Then next are coming alpha particles or helium-4, nuclei of helium-4, which compose around 10%, and the remaining less than 1% includes heavier species up to iron nuclei and beyond, and also some antimatter in the form of antiprotons. Just going a bit ahead, that no other antimatter has been found in cosmic rays so far. So there are plenty of antiprotons, but not a single antihelium have been confirmedly found in cosmic rays. They are all of extraterrestrial origin, which includes sun, stars, neutron star, black holes, supernova, active galactic nuclei, radio galaxies, etc. A whole bunch of energetic phenomena in space, but they're all extraterrestrial. Energetic particles of terrestrial origin are not considered as cosmic rays. This includes, for instance, magnetospheric particles, auroral electrons, and others. They are highly energetic. The most energetic cosmic rays may have energy up to 10 to power of 20 electron volts, which is equal to around 20 joules of energy. And this is just to compare, this is a kinetic energy of a baseball ball hit by a good player. And all this energy is contained in a tiny nucleonic particles. This is really huge energy. Density near Earth is quite small. If we just take a number density or make a snapshot and count cosmic rays in 1 cubic centimeter, we would find that the density is around 10 to minus 10 cubic centimeter, or 1 particle in 10,000 cubic meters in space near Earth. This is very small density, but they are highly energetic, and this means that the energy density is around 1 electron volt in cubic centimeter, and this is quite sensible energy. This should be really compared. Also, although the number density is quite small, since they're very energetic and thus travel with very high velocity close to the speed of light, their flux is not negligible. It's around 1 particle per square centimeter per second in space near Earth. However, on Earth, we are quite well protected by the geomagnetic field and the atmosphere above us, and flux of particles coming from originating from cosmic rays is around 1 particle per square meter per second, which means that it's around a factor of 10,000 reduction of flux in space and on ground, implying a very effective protection of us on ground from the hazardous cosmic radiation. As said, the composition of cosmic rays is very broad, from hydrogen nuclei to iron and beyond. As you can see, there is also nickel, zinc, and germanium. The red curve here shows, I don't know if you see my pointer, the red curve shows the composition of cosmic rays, and the blue one is the so-called universal abundance, which is also typical for solar system, for instance. As you can see, they're quite similar, except there is an excess of some elements, including light elements, lithium, beryllium, and boron, in cosmic rays with respect to the universal abundance. And this is explained by the fact that these elements are secondary. So they are produced by cosmic rays in interaction with, for instance, carbon, nitrogen, or oxygen in the galaxy, producing spallation reactions where lighter elements like lithium, beryllium, and boron can be produced. Other elements are mostly primary, and they have the composition quite similar to the universal, which means that they are not produced in some special reactions. They're just accelerated particles of the normal composition. It is believed presently that the main source of cosmic rays as observed near Earth are remnants of supernova, where cosmic rays can be accelerated to high energies up to about 10 to 15, 10 to 16 electron volts. And there are very well developed theoretical models, but also there are direct indication of that fact. And one example is shown here. This is an image of supernova 1006, remnant in two wavelengths. One is the red curve is the soft X-rays from heated gas. So this means very hot temperature, and this is a reverse shock from the supernova explosion shock. So the red shows the very hot temperature where this supernova explosion shock now exists, and the blue color indicates harder X-ray, which are produced by high energy particles, mostly electrons. As you can see, the two images exactly coincide, which indicates that energetic particles are accelerated exactly at the shock related to this supernova remnant. There are other examples like that. So the paradigm is that cosmic rays, at least up to some quite high energy, are typically accelerated by shocks produced during supernova explosions. So there are, of course, many supernova remnants in the galaxy. Now I'm speaking of our galaxy, of the Milky Way galaxy. And once energetic particles have been accelerated to high energy, they can leave the region where they have been accelerated, and then they start propagating in the galaxy. Because of the our galaxy has a magnetic field, and it's quite inhomogeneous. The transport of cosmic rays looks like a diffusion. So they don't go in a straight line, like, for instance, light, but they do scatter on magnetic inhomogeneities, slowly diffusing in the hollow and then galactic disk, so that a typical diffusion time of cosmic rays in a galaxy is around several millions of years. So, which means that the cosmic rays which we observe on Earth were on average produced several millions of years ago, and they diffused in the galaxy before reaching us. This also implies that they lose entirely the direction from where they come. So for normal galactic cosmic rays, cosmic ray astronomy cannot be made because the direction is lost. However, for the ultra high energy cosmic rays, it is still possible because their energy is so high that they can ignore the magnetic field of the galaxy. Also, I would like to mention here that the diffusion is mostly due to the scattering on magnetic irregularities. It is not scattering on matter or collisions with other particles. It's mostly because of the magnetic field. So what we observe at Earth are cosmic rays with different energy. So we can discuss the energy spectrum, or sometimes it's called intensity, which is the flux of particles per square meter per steradian per second per giga-electron volt as a function of their kinetic energy. We always speak of kinetic energy here, not of the total energy. So as you can see, as I said in the very beginning, that the average flux of cosmic rays near Earth is about 1 particle per square centimeter per second. And this is for the lower energy cosmic rays, whose energy is around 1 giga-electron volt. There are, of course, much higher energy particles, but their flux is lower. It decreases nearly as a power law with a spectral index of -2.7. And this leads to the fact that at the energy of around 100 giga-electron volts, the flux is 1 particle per square meter per second. At so-called knee region, around 10 to 15 electron volts, the flux is 1 particle per square meter per year. And at the highest energy, the flux is 1 particle per square kilometer per year. Now just try to think how to measure such fluxes, where it's 1 particle per square kilometer per year. So either you need huge detector of many square kilometers area, or you need to wait for hundreds of years to get good statistics. We will come a bit later to that point. What we do next, as said, the spectrum is nearly power law, but it's not exactly power law. Just to see it, we now can multiply the spectrum with the energy in the power 2.7 to remove the power law, and what remains is here, and we see quite interesting structure. So up to energy of around 10 to 15, 10 to 16 electron volt, the spectrum is flat, which means it's power law with the index of 2.7, and then there is a break in power, getting it's around -3, and it's called knee of the spectrum. It goes like that, and then it becomes flatter again at energy around 10 to 19 electron volts. It's called the ankle of the spectrum. Just to explain these terms, I show this a human leg with knee and ankle. And then above the energy 10 to 20 electron volts, there is so-called JZK cutoff, so that we do not expect to measure at Earth particles with energy above that, even though they can be accelerated to higher energy because of the resonant interaction of these particles with the galactic microwave background. We don't expect to see much of these particles. Then there is some indication not clear of the second knee, which we actually don't like to have, at least at the human leg, a second knee, but that's still disputable. The main feature is that there is a knee or softening of the spectrum, and then again hardening as an ankle. You can actually see it also in the original spectrum, where this is a knee and this is an ankle. It's hard to see, so that's why it's applied this method. Very briefly, a paradigm is that up to the knee, up to 10 to 15, 10 to 16 electron volts, acceleration by supernova remnants in the galaxy is very efficient, and then it becomes less efficient, or there is just a fewer number of sufficiently energetic supernova, and then at energy about of 10 to 19 electron volts, extragalactic sources of cosmic rays start to dominate, and this makes the spectrum harder again. So the most energetic particles are likely coming not from our galaxy, but from far beyond that. To summarize the facts about cosmic rays, is that cosmic rays are accelerated mostly in supernova remnants up to some maximum energy, and they can be reaccelerated in magnetic clouds, for instance, during their way. They are trapped in the galaxy due to its magnetic field, where they diffuse for several millions of years. Cosmic rays of ultra-high energy are mostly of extragalactic origin, because in our galaxy we don't have sources which could accelerate cosmic rays to 10 to 19, 10 to 20 electron volts. The knee of the spectrum is due to less effective acceleration and or propagation effect in the galaxy. The ankle is believed to be transition from galactic to extragalactic cosmic rays, and the rays in Zatsepin-Kuzmin cutoff, due to the interaction with cosmic microwave background, limits the flux at energies above 10 to 20 electron volts. Another factor important for us on Earth is that the Earth has its magnetic field, which actually shields us from at least lower energy part of cosmic rays, so that they cannot penetrate the Earth atmosphere in large areas around the tropics, and can only penetrate interpolar areas, which are quite small geometrically, implying that the overall reduction of the flux of cosmic rays at Earth on the top of the atmosphere, comparing to the flux in the open space, is quite significant. Now we will discuss more about studies of cosmic rays. And here, for cosmic ray physics, there are actually three different aspects what we can do. One is nuclear physics, when cosmic rays form an object of research. And this is because of their high energy. Energy of most energetic cosmic rays is not reachable in laboratory experiment, even in the colliders. So the nature provides us with the particles of extremely high energy, which cannot be reached in laboratory experiments. But still, we can study physics or nuclear physics at very high energy. Then cosmic rays can be a tool for research, and this is related to astrophysics and cosmology, as composition of cosmic rays is directly related to cosmology and astrophysics and can be used to validate some model. Their origin is a probe for energetic phenomenon in space, especially if applying multi-messenger studies, and their transport in the galaxy or in the solar system is a probe for parameters of the matter and magnetic fields in those regions. And finally, cosmic rays can be subjects of study, and this is applied to geophysics and space physics, where we study the effects of cosmic rays produced on atmospheric properties. What I was telling so far was about galactic cosmic rays, which are omnipresent near Earth. They're always there with a slight modulation in time, but sometimes there are sporadic events when solar energetic particles can be observed. And an example is shown here. This is a period of the famous Bastille Day events of the year 2000. Bastille Day is July 14th, when there was a flare, as shown on the green picture, and a coronal mass ejection shown in the blue picture, as you can see. But what is important here is that after flare, and especially after coronal mass ejection, the image is actually spoiled by white spots. Sometimes they are called snowflakes. These are charged particles which hit the CCD camera, making an image of the sun. And this is just to visualize that after a solar flare or coronal mass ejection, there is a big flux of charged particles in space, which actually blinds the CCD camera, just not intended for that. But what is noise? Here, for optical or for CCD imagers, is a signal for us, because these are cosmic energetic particles produced, accelerated during solar flares and coronal mass ejections, and they're called solar energetic particles. And an example is shown here. This is a count rate of a ground-based neutron monitor located in Oulu, in a city where I work and live. And as you can see, this was in January 2005. There was quite stable period of galactic cosmic rays nearly constant. Then there was variability at the level of 15%, roughly, and at some moment there was a huge spike of around 150% increase, which lasted for several hours, and then it disappears. This was one of the strongest solar energetic particle events detected by ground-based instruments. This is called ground level enhancement. And again, it was in Oulu, it was around 150%, but in another polar station, it was around several thousand%, which means an increase of galactic cosmic ray background by a factor of 20-30. This is a huge increase, which may have serious consequences, but from historical indirect proxy data, we know that even more extreme solar energetic particle events occurred in the past during the last millennia, which were at least 100 times stronger than this one. And just to compare here, I show this blue bar on the right is the strongest ever recorded solar energetic particle events, which occur in January of the year 1956, which is unity on this plot. And this is the strongest historically known extreme solar energetic particle event, which took place in the year 774 AD, which was a factor of 70 plus minus 30 stronger than the strongest directly observed event. And we wouldn't like it to appear again now, because such event would be so strong, the flux of energetic particles would be so dramatic that most likely we would instantly lose all our satellite fleet. So we would lose communication and navigation satellites instantly. But the good news is that such events occurs once in a 1 or 2 millennia. So the probability is not very high. Okay, I promised to tell you how we can measure cosmic rays, which have actually around 30 orders of magnitude in flux and around 20 orders of magnitude in energy. This has shown the typical energy spectra of galactic cosmic rays, the red curve, and the blue curve is solar cosmic rays. Of course, it cannot be done with a single detector. We need different families of detectors. And just historically, first, we will start from measurements in space, which started in 1970s, and they covered energy up to around 100 mega electron volts. And this was mostly about solar energetic particles. Then since the year 2006, a very massive spectrometer appears in the orbit, and those can measure energy up to hundreds of giga electron volts, covering now galactic cosmic rays. There are some balloon measurements, but they are unfortunately only campaign-based. There are no permanent, of course, balloons. Then very important instrument since the year 1951, it's called neutron monitor, a ground-based detector which measures nucleonic component of cosmic rays. Then there are muon detectors, which cover a little bit higher energy, and they also exist since 1960s. And then there are high energy detectors since mostly 1990s, which cover the high energy range of the cosmic ray spectrum. This is an example of the most sophisticated cosmic ray detector in space. It's called alpha magnetic spectrometer. it's located in the International Space Station here, and a closer look is shown on the right. It's a huge detector. It weighs more than 8 tons without the frame. It takes around 64 cubic meters, has big power, 2.5 kilowatts, and very strong data downlink of around 10 megabits per second on average. It includes 15 different particle detectors and supporting some system, all working together. It was launched in 2018 and it's still on orbit, still worked. Initially, it was planned to work for several years, but presently it has been extended for another 4 years. So at least until 2028, or as long as the International Space Station stays in orbit, it will be operational. And cost is a couple of billions of dollars. So this is huge instrument. Okay, but it flies above the atmosphere. As I said, the Earth's atmosphere is very thick. It's and what happens inside is that when cosmic rays come to enters the atmosphere, it collides with one of the nuclei of atmospheric gases. Partly it can destroy it, producing fragments, or it can produce other particles like pions, which decays to gammas or muons, or secondary fragment can be still energetic, then collide again. And on the average, there are around 10 collisions before this called the atmospheric shower or cascade, before the secondary particles of this cascade can reach ground. This is very important to say that the primary cosmic rays which hit the atmosphere almost never reach ground. There are always secondary particles or subproducts of the atmospheric cascade, and this makes the atmosphere the detector of cosmic rays per se. And there are different types of detector which can measure this atmospheric cascade. For instance, it can measure fluorescence along the cascade, or Cherenkov light of the cascade, or it can be a huge array of muon detectors on the ground, which work in coincidence, so that indeed the effective area or volume of these detectors becomes huge, tens of square kilometers, and therefore even highest energy cosmic rays can be detected with such instrument. How do cosmic rays vary in time, or are they constant? First thing is that we are living in a solar system which is in a magnetohydrodynamic sense totally driven by the solar wind and solar magnetic field, forming the so-called heliosphere, which forms a bubble and obstacle for cosmic rays, or a bubble formed with solar magnetic field. And since cosmic rays are charged particle, they are affected by the heliosphere. And a transport equation of cosmic rays in the heliosphere is quite complex. I will not go into details, just to mention that there are four main mechanisms affecting cosmic ray transport in the heliosphere or any other area filled with magnetic field. It's convection by solar wind, it's drift in the inhomogeneous magnetic field, it's a diffusion due to the scattering on magnetic irregularities, and it's adiabatic cooling. Altogether, this equation cannot be solved analytically, but it can be solved numerically, and altogether it leads also to a diffusive propagation of cosmic rays inside the heliosphere. So they do not go straight as in the galaxy, I said, but they are scattering on magnetic irregularities, and it takes quite long time, actually up to several months, for them to reach Earth from the outer heliospheric boundary, because the propagation looks like a diffusion. All in all, it leads to the so-called heliospheric modulation of galactic cosmic rays near Earth. So when the solar activity is high, heliospheric magnetic field is stronger, the flux of cosmic rays near Earth is more suppressed, than vice versa. During solar minimum condition, the flux of cosmic ray is higher. During solar maximum conditions, it's weaker. So cosmic ray flux vary on different time scales, and on the time scale of days or hours, these are mostly transient phenomena originating from the sun. As I mentioned, these solar energetic particles. There can be also suppression of galactic cosmic rays due to the propagating coronal mass ejection as shocks, leading to so-called Forbush decreases, as clearly shown here. There are 3 Forbush decreases with a difference of several days. Then there is the famous 11-year solar cycle in cosmic ray variability near Earth, caused, as said, by solar activity. So when the solar activity is high, the flux of cosmic rays is lower, and it goes the same way every 11-year solar cycle. Then on a longer time scale, on centuries and millennia, the cosmic rays are affected by 2 main factors. Is geomagnetic field, which is observed here as a slow variability. Now it's on a time scale of 10,000 years. Slow variability is caused by the geomagnetic field, and shorter variability, shorter means hundreds of years, is changes of solar activity. And then finally, our solar system moves or rotates in the galaxy, sometimes being inside spiral arms, sometimes being in between. Now we are in between. And this also changes the flux of cosmic rays, because when we are in a spiral arm, there are more stars and supernova around, so the flux of cosmic rays is higher than when we are in between cosmic rays. Okay, now I will very briefly say what happens to cosmic rays in the atmosphere. As I said, cosmic rays form the main ionization factor of the atmosphere. There are other factors ionizing the Earth's atmosphere. So near ground, it's mostly radon and radioactivity of soil. There are also lightning strokes which can ionize air around them. There is solar radiation with ionized upper atmosphere, also energetic particle precipitation, mostly electrons, which also can ionize the upper polar atmosphere. But cosmic rays provide ionization everywhere. They can reach down to the ground. In polar tropical areas everywhere, they form the main source of ionization. As shown here, this is the mean ionization rate in the atmosphere as a function of the atmospheric depth or its pressure, barometric pressure, or approximate altitude, and the geomagnetic latitude. As you can see, the the highest ionization rate is in the polar atmosphere at the altitude of around 15 kilometers, and then it decreases towards ground, and it's less ionization in the tropical areas. If we put it now on the map, this is a typical map of the cosmic ray-induced ionization at the height of around 5 kilometers. Of course, the highest ionization rate is observed in polar regions when there is no geomagnetic shielding, and it's somewhat lower by a factor of 2 or 3 in the tropical region, in the equatorial region. This plot shows the ionization rate during the strong solar-energetic particle events. As you can see in the polar areas here and here, during the peak phase of event, the ionization rate can be enhanced by a factor of 1000 for several hours. This may have strong implication for the atmosphere, but it doesn't last long. It's only several hours. Even though I was speaking of the ionization by cosmic rays, of course, our atmosphere is mostly neutral. It's not plasma. The fractional ionization rate is around 10 to minus 18 per second, and considering the recombination rate, the degree of ionization in the atmosphere near ground is around 10 to minus 60. That means that it's essentially neutral, but there are ions, and it makes it quite important. And the final topic of the lecture is what happens with the atmosphere in the presence of cosmic rays. So, as said, the most direct effect of cosmic rays is the enhanced ionization. And it's especially strong in polar areas at the altitude of around 15 kilometers. And there have been several experiments measuring aerosols in the polar atmosphere as a function of altitude around the time of the strong solar-energetic particle events, as shown. Here, for instance, this is the aerosol extinction index, and as you can see, this is the time of the solar-energetic particle events at the height of around 15-20 kilometers. There was a strong production of aerosol in the polar atmosphere when the ionization was enhanced by a factor of roughly 1000. And this enhancement was not related to any temperature or other effects. So it's believed that this is direct effect of the ionization. Another process on which the cosmic ray-induced ionization can affect is the global electric system of the Earth. When there is enhanced ionization, this of course increases the conductivity of air, and this leads to enhanced vertical electron current in the global system, as indicated here. For instance, in this plot, so this is the effect of cosmic rays, which can enhance the global electric current. And coming to the summary of my talk is that cosmic rays include several species, mostly galactic cosmic rays, which are omnipresent, sporadic solar cosmic rays, which can be very high in fluxes by short in duration. I didn't mention the anomalous cosmic rays, but they are usually not important for the atmosphere. They are all different in sources, energy spectral, and temporal variability. The most important effect is that cosmic rays induce a complicated cascade or shower in the atmosphere, whose products can reach deep layers of the atmosphere and actually ground, and they can ionize air along the cascade. And cosmic rays form the main source of atmospheric ionization, which leads to physical chemical changes in the low and middle atmosphere, especially in polar region. The direct effect of cosmic rays on the atmosphere is weak, but it is observable. Indirect effect is unknown and still discussed. Thank you very much for your attention.
Thank you very much for the interesting lecture. So I think there is time now for questions. So if anybody has a question, please raise your hands. There are some clapping, virtual clapping hands, but yes, so if you want, you can also unmute yourselves to ask a question. I can ask one until I see somebody raising their hands. So you mentioned also something about the detector AMS, which is going to be flying or operating.
It is flying.
Yes, it is flying. Yes, but you mentioned that the lifetime is going to be similar to that of ISS, obviously, yes, like the maximum one. So the question is there? Are you aware of any other like experiment that is being planned in order to, I don't know, take over when AMS is not going to be operating?
No, there have been another little bit smaller experiment of that kind, Pamela, who was in operation from 2006 to 2016 for 10 years, but it was lost in 2016. No, I haven't heard of any other dedicated experiment of that size to measure cosmic rays in space.
Yes. Oh, that's unfortunate because yes, AMS has done it.
AMS is wonderful, but it's very expensive, very big, and very complex too.
Yes, thank you. I see one hand raised by Professor Mastichiadis.
Yeah, hello.
Hello.
Thank you very much for your talk. It was very clear, so it's not really a question, but it's something like to start the discussion. You mentioned about the size of particle of cosmic ray acceleration, and you said about supernova 1006. Now, this supernova, we know it accelerates electrons, not protons. So, in my mind, it's not 100% sure yet whether we have nuclei accelerated in supernova environments. Of course, smoking gun is there. Okay, so there are some gamma ray detections, but I think that there is still a small possibility that, you know, we see electrons radiating, but protons might be more difficult to, or cosmic ray nuclei might be more difficult to identify. What's your opinion on that?
You are right. What we see is radiation from electrons, because from protons or heavier species, we would not see that clear radiation exactly at the site of acceleration. But the idea is that when electrons are accelerated, protons are also accelerated. Of course, since they are more than 2,000 times heavier, it's more difficult to accelerate them. So in this sense, yes, you're right. I said that this is a clear evidence of acceleration, but I didn't say it was acceleration of protons. We see only acceleration of electrons. We cannot really see the acceleration of protons or heavier species. That's true.
Okay, yeah, thank you. I think they try to find the sites by, by zeros, and which are produced from proton-proton collisions, but it's not so clear cut yet as it is in
Yes.
X-rays from electron synchrotron. So
yes.
yeah, okay, thank you.
Yeah, and they're mostly collisionless, and so it's the rate of collision is very low for protons. For electrons, that's synchrotron or Bremsstrahlung, it's easier to observe. Yes, I agree. Again, I agree with you that it's very difficult to observe directly. But on the sun, for instance, we see very clearly signs of acceleration of protons in solar flares. But that's beyond this lecture.
Okay, thank you.
Are there any other questions? So I may have one until there is somebody who wants to raise their hands. So you mentioned something that anti-helium has not been detected so far. So what's the leading theory behind the non-detection of anti-helium in nearby Earth?
Yeah. Okay. So I will start from antiprotons, which have been detected in quite big amount by AMS, but they have been discovered even before that from balloon experiments. The question was always been whether these antiprotons are secondary, which means they are produced during collisions of primary cosmic rays during their transport in the galaxy, or they are primary, which means really antimatter. So far, there is no, so far it's more or less consistent with the purely secondary production. And with anti-helium and especially anti-carbon, for instance, if the statistics of IMS, the whole statistics of IMS collected so far is such that, if I remember correctly, maybe I'm wrong, but not too much, it should have been detected about 1.5 of anti-helium during the entire statistics of IMS if it's secondary. So if several anti-helium would have been observed, it would clearly indicate direct antimatter in our galaxy. But the fact that it's not observed doesn't say anything yet.
Yes, it's very close to, it's consistent with.
Yes, yeah.
Okay, thank you. Are there any other questions for our speaker? If not, I think it's time to say goodbye, and thank you very much for this very clear and pedagogical lecture.
Thank you.
Thank you. And to the rest of the audience, see you next Wednesday with a talk about Jupiter.
Okay. Bye.
Thank you very much. Bye.